I'm going to apologize to no Spanish speakers. I'm going to make the introduction in Spanish. Henri Gillet es un especialista en geometría algebraica y también un poquito de números. Trabaja en ambas áreas y hay una unión entre las dos cosas que se llama geometría aritmética, geometría algebraica aritmética. Y él junto con Soule, francés, VHS, generaron toda una teoría que se conoce, teoría de Arakelov. Hicieron bastantes trabajos, crearon toda una teoría al respecto, una teoría de intersección para variedades aritméticas, etc. Y también desarrollan un teorema muy importante que se conocía antes desde otros puntos de vista, que fue el teorema de Riemann-Roch, un trabajo conjunto de ellos que tiene consecuencias muy importantes en ambos campos, digamos. Él trabaja en la Universidad de Illinois en Chicago desde hace muchos años. Y ha venido a México ya varias veces. En la Ciudad de México la última vez estuvo en 95 en un congreso que organizó el ministro de papelería, también para las papelerías. Pero en Guanajuato, que hemos organizado otros eventos, pues ha venido varias veces a visitarnos. Entonces es un visitante de México. Plática es su primera plática de 3 que va a dar, es un mini curso que está dando en el congreso donde estamos, aquí junto en el salón. Esta es la primera de 3 pláticas que va a dar, mañana va a dar las otras 2.
Thank you. I have to say it's a great pleasure to be back in Mexico City. Well, I've been in Mexico a couple of times since then. The last time I was here in Mexico City and at UNAM was in November, December, I think it was, of 1985. So, it's a pleasure to be back. So what I'm going to talk about today is really to give, I'm giving a series of 3 lectures in this workshop, and this lecture will really just be an overview of some problems in arithmetic geometry, some very well-known problems, and some indication of how they, hopefully, how they fit together with what I'll be talking about in the next couple of lectures. And I think this is always, especially if we have an audience which is not necessarily familiar with these questions, it's always an interesting story to tell about the relationship between geometry and questions in number theory and arithmetic. So I really want to start with the Mordell conjecture. Which was formulated in 1922 and then was proved by Faltings in 1983. And this says the following. So K is a number field. So i.e. K is a finite extension of rational numbers. And if X is a smooth projective curve over K, I'm going to explain what I mean by this in just one second. Or G is G at least 2. Then X of K is finite. So what do I mean by this? Well, let me actually give an example first. So by smooth projective curve, what I mean is a set of solutions let's say for the moment of a homogeneous polynomial, or maybe I should say a system of homogeneous polynomials fi x0 through xn, which are in, let's say initially, let's take these polynomials to have complex coefficients. And since these polynomials are homogeneous, we'll identify solutions of A0, AN is a solution, we'll identify that with lambda is a non-zero complex number. So in fact, what I've described here, let me actually erase curve here and just say, let's just say projective. Well, let's just say it's a variety. But let me start with a very simple example. So the example I have in mind comes from Fermat's last theorem. So as hopefully everybody knows, Fermat's last theorem has to do with the solutions to the following equation. It goes x to the n plus y to the n equals z to the n. So this is clearly a homogeneous equation. So it's homogeneous. And I should have said here, a set of solutions where we want solutions that we exclude. So this is what's called a trivial solution. Anytime you have a homogeneous polynomial, set of solutions are, I should say, of f of x0, fi x0, xn equals 0. So as you have a system of homogeneous polynomials, we're interested in the equations fi of x equals 0. Anytime you have a homogeneous equation, just setting all the variables to 0 certainly gives you a solution, so you're not interested in that. Anytime you have a solution, you multiply by a non-zero scalar, you get another solution, so you think of those as being the same solution. So if we look here at this equation, we will identify, well, if I have a solution A, B, C of this, let's say, so A to the n plus B to the n equals C to the n, we view that as the same. Okay. Now, in Fermat's last theorem, what we're really interested in is solutions where x, y, and z are integers. But if you find solutions which are integers, since we're allowed to multiply by any non-zero scalar, it's sort of equivalent find solutions A, B, C with A, B, C rational numbers. Because if I find a triple of rational numbers, let's say the rational number is maybe R over S to the n plus T over U to the n equals V over W to the n. So this is R over S, etc. But R, now R, S, T, U, V, W are integers. then I just multiply through So in other words, to find since the equation is homogeneous, integer solutions are the same as rational solutions. Okay, so I mean, to really sort of revisit a completely elementary story, how do we find, let's say, when n equals 2, there are infinitely many solutions. Well, how do you find these solutions? Well, you replace any time you have a homogeneous equation, you can replace this by an equation which is not homogeneous, so long as you want to exclude the possibility that one of the variables is 0. So let's write this as little x to the n and we look at this equation. So, well, there's some obvious solutions. So those correspond to finding solutions over here, which are 0, 1, 0, 1, 0, 1, 1. And now I can find any other solution by taking a line through this point here, where the slope is a rational number, and then this point here, this will have coordinates and these will both be rational. Well, maybe let me just write this as, say, A and B. So it's a trivial exercise to show that A and B have to be rational. And so this implies that AB is a solution of x squared plus y squared equals 1. So you get an infinite family of solutions of Fermat's law, of the Fermat equation when n equals 2. Okay, so this is the circle. It's a very simple curve. If I look at n greater than 2, when n is greater than 2, what happens? Well, you could simply naively try drawing the same, drawing the curve. So let's say if n equals 3, you get a curve which looks like this. If n equals 4, you get sort of a flattened circle, and the same argument fails. In other words, taking straight lines through some point doesn't give you more solutions. So what might be happening here? So the Mordell conjecture really had to do with the situation in which, let's, for simplicity, assume we have So I have a homogeneous polynomial in 3 variables, where I can think of my number field as sitting inside the complex numbers. Then I can look at the solutions of this homogeneous polynomial and its associated, so I look at the solutions of this homogeneous polynomial over various fields. I look at the solutions over K or over C. So let me just say that more or less, well, so number 1, an affine equation, that's, let's say, I have something like f of x, y, 1 equals 0. If I look, let's suppose the k is actually contained in the reals. Here's a curve in R2. But the homogeneous equation gives, well, a curve over C, but actually, let's say, skip a little step here after resolving singularities. Gives a Riemann surface. So look at the set of solutions and make this identification with 2 solutions which are the same, which are, if you get one another by multiplying by a non-zero complex number, I view them as the same. Then the set of such solutions is a Riemann surface. And so the number of holes so it turns out, so this is genus 0, genus 1, genus at least 2. If I go back to the Fermat equation, so x squared plus y squared equals 1, or in other words, x squared plus y squared equals z squared, actually is this case. This is actually the case, sorry, n equals 3, and this is the case for large n. And so Fermat's last theorem, which was then proved by Andrew Wiles, Mordell's conjecture as proved by Faltings, the Fermat equation has finitely many solutions. In other words, these equations have rational coefficients, but once the associated curve has genus at least 2, then Mordell's conjecture, theorem of Faltings, says that the number of solutions is finite. So in other words, Mordell conjecture asserts that the sort of geometry of the set, the solutions of the system Fi over the complex numbers controls the finiteness of the solutions of the system Fi over the number field K. When X is a curve. Okay. Now, a key remark, from the point of view of geometry, maybe I should even say from the point of view of complex geometry, so one of the differences between these three cases is not simply that it's the number of holes, but it has to do with, if you like, the differential geometric properties of these three classes of surfaces. In other words, these ones are hyperbolic. So they have metrics of negative curvature. This actually has a flat metric. Let me actually erase. And this has positive curvature. So it's even more tantalizing is there really seems to be some strong connection between the curvature properties of the manifold complex solutions of a system of equations and the arithmetic properties. So when I say geometry, this really say, at least in the case of curves, and as we'll see potentially indicate in higher dimensions, really reflects not simply in some sense the number of holes, it has something to do with the differential geometric properties of these manifolds. Okay. So there's something called geometric analog. For the Mordell conjecture, which you can replace. So I mean, I should say for people who don't really know algebraic geometry, the genus here can be given can be defined purely algebraically. So in other words, it's really just a property of the system of equations as an algebraic entity. You don't actually have to go and look at the associated complex manifold. So that means potentially you can talk about this question when you have fields other than complex numbers. So now let K be any field. Well, I'm going to say something somewhat nebulous here, with properties similar to a number field, and by that I mean the following. So a number field, remember, has its ring of integers. In other words, a subring consisting of elements of the field which satisfy integral equations with integer coefficients. Now, this ring is a Dedekind domain. So, in particular, if P is a prime ideal, then the localization of this ring at this prime is a discrete valuation ring. So if I just look at sort of these conditions right here, Well, I can in fact take an example, sort of very simple example of a genetic domain, is to take K a field, and look at polynomials in one variable over that field. And so going back to Hasse, there's this idea, there's an analogy between polynomials, sort of anybody who's taken the first course in abstract algebra, at some point learns that K of t is a Euclidean domain and has properties very similar to the integers. And so there's an analogy between then K of t, the field of rational functions, and Q, and K a number field, and K a field which is a finite extension of K of t. And so we can actually ask exactly the same question. In other words, you just look at an equation, let's say in one equation in three variables over this field K. So in fact, it's very easy. Sorry, I shouldn't start. So K, so this is what's called now, so K is a function field. So K is a function field. That means that and if well, I'm just going to say if x, well, I say if x is a smooth projective curve over K of genus at least 2, then x of K is finite. Well, there, if you think about it for a second, this doesn't quite make sense because I haven't told you anything about this field K. So there, if I simply take potentially I can take lots of different values of t here and get lots of points. So the real, you have to say here, x of K is finite, or there's a curve y over little k such that x is, well, another way of saying it, i.e., x is given by an equation with coefficients in K. And now I have to be a little bit careful because this is not quite true.
You mean the small k or big k? Small k.
Yes, thank you. Yes. Well, this is let's say by replacing K and replacing x by an isomorphic curve. So if I think of this in terms of saying, thinking of a curve as being given by a single equation in three variables, roughly speaking, then you can pretty quickly come up with the idea that different curves are isomorphic in the sense that you can prove you're going to have exactly the same solutions. And so what this says is, well, maybe x is given by an equation with coefficients in small k, but after replacing big K potentially by a larger field, and then replacing the equation by an equivalent equation, you actually get an equation with coefficients in little k. And when that happens, you can actually show that you will necessarily get infinitely many solutions in general. So, okay, so geometric Mordell say something like this. This actually has a sort of a really geometric interpretation. After all, this ring here is the ring of functions. This is polynomial functions. Just on the affine line, on the line. And so I can think of, in fact, where to go? Yeah, here. K, this function field, this is actually the field of functions on the curve. And so one way to think about this, let's say if little k equals c, in particular, where it's sort of easier to visualize, is you start with k being a curve in the sense we were talking about before. So k being the function field of the curve. So you have k. Let's see k over here. You have this curve which is given by essentially a single equation, was equivalent to something, was determined by something given by sort of a single equation and 3 variables over k. On the other hand, k can be thought of as, since k is an extension of little k of t, since little k is the complex numbers, this is a finite extension of fields of characteristic 0, and therefore is primitive. And so actually you can describe this by a single equation in 3 variables. You actually get a curve here. It's a curve with field of rational functions equal to k. I should say it's an affine curve. And now this x here corresponds to this here. This is now a family of curves. Whereas here you have a curve. I mean, it's a curve over the complex numbers. So I'm not going to be, well, maybe I will do this. And there are some points missing. And then over everywhere, except for these points, you now have so this is actually a 4-dimensional object. 4 real dimensional. And now the thing is that point solutions, so you basically get this just by looking at the equation for this curve, essentially looking at, sort of making it into an equation in 4 variables. Wait, I may probably not count the number of variables correctly. One has to be an equation in 6 variables. But the important point here is that now you have this very geometric object. You have a complex manifold down here, you have a family of complex manifolds. And the key thing is here, points here, so solutions here, so points, they correspond to sections. And so what what geometric Mordell says is more or less equivalent to the following statement. is really equivalent to the following statement. So if C is an affine curve, over complex numbers, so here's C. And let's say pi from X to C is a submersion of complex manifolds. With fibers Riemann surfaces of genus these two. Then if the family has infinitely many sections, it is trivial, i.e. product, possibly after passing to a cover C prime to C. So i.e. X cross C, C prime is isomorphic to C prime cross Y, where Y is just a Riemann surface. So that's geometric model. So there are really two parts to proving this. You need a criterion for when a family is actually trivial. You need some, just forgetting about whether there are sections or not. You need some way to tell whether it's trivial. Because the answer to that is given by the, essentially, in this case, by the Kodara-Spencer class. So, the Kodara-Spencer class, well, if I look at this family here, so I have this manifold mapping down smooth by submersion to this other manifold. I get, so look at this mapping name, pi. I get this exact sequence of this tangent bundle exact sequence. And in fact, since this is an affine curve, and I actually don't care, I can make this curve smaller. I'm going to assume here, without loss of generality, so i.e. there exists a non-vanishing vector field on the base curve. So this is actually now an extension, so this is really just isomorphic to the trivial one. And so you get a class let's call it the Kodara-Spencer class. And the theorem, so there are various proofs of this, which I won't go into, at least for the moment, but I mean, the theorem is that in characteristic 0, Kodara-Spencer class trivial implies, so this condition right here is called isotriviality. Let me try and write this. Isotrivial. So it's not quite trivial, but it's trivial after passing to a finite cover. In characteristic 0, Kadar-Spencer class trivial as a cohomology class implies the family is isotrivial. Now, what does the Kadar-Spencer class trivial mean? We've got this vector field. So this is equivalent to saying that delta lifts to a vector field delta tilde on X. And rather than prove this theorem, I sort of draw a picture. So here's the base, and here's our vector field delta. Here's our family. Now, if we can lift the vector field, then that saves we've got a vector field like this upstairs. Now, the existence theorem for solutions of ordinary differential equations. So if delta lifts X, this is actually complex analytically trivial, or I should say locally trivial. In other words, we just flow along these lines and nearby fibers become isomorphic. And it's, you have to make that that statement algebraic to get the statement that I had over there. I'm not going to explain how we do that. But anyway. So let me just say a few words about the proof of geometric Mordell. Maybe not so much about the proof exactly, but so geometric Mordell it then becomes if x of k is infinite, then that implies that the Kadar-Spencer class is trivial. So that's really what you want to prove. You want to go from having an infinite number of points to the triviality of the Kadar-Spencer class. I should mention in passing that there really is no analog that we know of the Kadar-Spencer class in the arithmetic case, in the case of the classical Mordell projection. So there were two proofs by Manin. Let me just check the date. 1963. And Grauert, 1965. Though Manin's proof actually had a little bit of an error in it. I don't know if that's an oxymoron, which was fixed by Coleman in 1990. Oddly enough, given that Grauert's an analyst and Manin is more of an algebraist, this is really the more purely algebraic geometry proof. And I'm not sure I quite want to say, so it's really Grauert's proof that I'm interested in. Let me just say Grauert's proof uses the following fact. If I have a Riemann surface over a field, so I have X is a Riemann surface over a field K, and the genus is at least 2. In fact, this is a criterion for the Riemann surface to be the genus at least 2. This says if I look at the tangent bundle, there is a map from the tangent bundle to affine space, called phi. And this map is proper, the fibers are compact. Phi of the 0 section is a point and phi is finite away from the zero section. So this is Grouart's criterion of openness. And you can use this, I mean, this basically, I won't go into the details at all, but you can use Grouart's criterion of openness to in fact produce a splitting of Kadara-Spencer, a splitting of this exact sequence order to prove the Kadara-Spencer class is trivial. Now, what can we say more generally sort of about geometric Mordell? So let's see. So generalizations. So the first generalization is when K is characteristic P. And that was proved by Samuel, I think maybe just a year, maybe pretty much immediately. Yeah. I mean, basically also in 1965, sorry. And the key point, what Grouart's proof construction actually does is it constructs, let me write it here, an X, you have X, and now it constructs a purely inseparable cover of X prime, such that when you pull the Kadara-Spencer class back to X prime, it becomes trivial. And what Samuel's proof showed that in fact, X prime is actually isomorphic to X. In other words, in the mechanism of Grouart's proof, you can actually trivialize the Kadara-Spencer class on X itself. And that's the key point. Second generalization, instead of going to characteristic P, dimension of X greater than 1. And so now here I just should say, so what's the right generalization of the genus at least 2? So here we have the Bombieri-Lang conjecture. That if the canonical bundle of X is ample, which basically means I'll just say X gives you so it determines a map which is generically finite. But basically, it really is sort of it's some kind of negative curvature condition on X. Then X of K is not dense. If K is a number field, okay, so in other words, if you have a curve, then the only way a set of points in the curve fails to be dense is if it's finite. Here the analog is that K, we don't require that K be finite, but that K can't actually be dense in the whole of X. So K, the closure of the set of rational points is actually, the heuristic closure is a proper subvariety. And if K is a function field, then X of K dense implies that X is isotrivial. So in this sense over here. So it becomes trivial after you pass some finite extension of K. Now, and almost nothing is known about these cases. There is a very striking result of faultings. I think the strongest results by faultings we prove something called the Mordell-Lang conjecture, which in essence proves this result for any subvariety. Let's say a subvariety of an abelian variety. So if you have a subvariety of an abelian variety, which is so I should have said here, so this is, I should say, I didn't mean something. X is of general type. So if you have a subvariety of an abelian variety of general type, then this result of faultings. So you have faultings proof. What's called the Mordell-Lang conjecture. So X inside an abelian variety. But in general, very little is known. So there's also a proof in characteristic 0. There's a theorem of Noguchi, and then Martin. Deschamps, which is if the cotangent bundle is ample, and that implies Bombieri line. I want to emphasize this is a much stronger condition than say general type. It's even much stronger than the thing I wrote erroneously than to say the canonical bundle is ample, because the canonical bundle is the top exterior of this. So you have progressively stronger negative curvature conditions, and this is just a very, very strong negative curvature. This was open, in characteristic P, this is from, let's see, let me finish up here by giving the dates, but this is, Noguchi is 81, this is 84. The characteristic P case has been open. And there's some recent work of myself and Daniel Rossler in which we've used the theory of higher derivations and I should say this is a preprint which has not been fully and carefully reviewed, so I should be, this is, let's say, tentative here. To prove the Noguchi Martin Deschamps result in characteristic P. And let me just mention that the fundamental problem in characteristic P, and this applied both in Samuel and here, so one fundamental issue is that the triviality of the Dada-Spencer class does not imply a priori that the family is isotrivial. Now I'll just make a very cryptic remark to explain that. And the reason is, if you go back to sort of the existence theorem for ODEs, I want to make you think about it. When you go to prove, if you know the Dada-Spencer class is trivial, you know you've lifted your vector field, and now you want to integrate the vector field. Now to integrate a vector field completely formally, you can do that using formal power series. So I'm sort of finish by saying that the reason this doesn't work in characteristic P you cannot formally integrate vector fields. Since you cannot divide by p factorial. And I'll finish there.
Any questions?
¿Qué cosa en español?
Yo también lo traducí.
Ahora, en el caso de que tienes una ecuación que tenga g igual que 2, ¿puedo usar la geometría hiperbólica para tratar de encontrar explícitamente las soluciones?
¿La geometría hiperbólica para qué?
Para encontrar explícitamente las soluciones.
He asked if you have a genus greater than or equal than 2, you can use hyperbolic geometry to find a explicit solution or something like that.
That's a very interesting question. Yeah, I mean, I mentioned this business of hyperbolic, that these things are hyperbolic manifolds. It is a great mystery why it is that hyperbolicity should control the solutions. And so it is really not understood, I think, is a fair statement. I mean, yes, in Grauer's proof, you have Grauer's criterion for ampleness. But I should mention, Bombieri-Lang has a purely geometric analog, which is, since I didn't really think about this, I may misstate it. But, so there are statements like this that, let me just give a very simple statement. If X of genus at least 2, if it's a Riemann surface, and I take just a holomorphic map, and now I have the universal cover of this is the unit disk. And there are no non-constant holomorphic maps to unit disk. And so this is sort of a proof by hyperbolic geometry that this thing that this F does not exist. And there are both theorems and conjectures in higher dimensions which say that by a variety of general type, then there, sort of statements about when the do and do not exist, non-constant holomorphic maps in complex numbers into such a variety. And so the very same varieties which you expect finiteness or at least non-denseness of rational points are also the varieties which you expect to have these very strong geometric hyperbolicity properties. And the relationship between these is sort of very deep. Let me just say, if you go look at what are called Voiter conjectures. So this analog between Neven-Limmer theory and Diophantine approximation. So yeah, it's very little is known about this.
Any more questions?